The next topic is stresses in curved beams. Now, from the data handbook, chapter number 25, in that figure number 25.12, you can see this sketch. This is a curved beam, this is inner fiber, outer fiber, and this is central axis, center of the geometry, and then neutral axis. The neutral axis always lies between central axis and the center of curvature. Now, when the curved beam is subject to an external bending moment, MB, now above the neutral axis, the fiber undergoes compression. Below the neutral axis, fiber undergoes tension. So, if you pass an arbitrary cutting plane, you can see the rectangular cross section. This is the inner fiber, outer fiber, the central axis, and the neutral axis. Now, consider a small portion by passing in two arbitrary cutting plane. One is AB, another one is CD. Consider in that small portion in the curved beam. In that small portion, consider a small element of at a distance of y from neutral axis y, and thickness of the element is dy. When you view from the side view, now this area of the element is dA at a distance of y from the neutral axis. Now, before going to determine stresses in curved beams, some of the assumptions we should take place. As you know that what are the assumptions? The first one is the material is homogeneous and isotropy. It obeys Hooke's law. On the cross section, when you pass an axis symmetry of the plane along the length of the beam, it remains cross section. It is even after subject to an action, before applying a load, after applying load also, the plane remains a plane. Then each layer of the beam is free to expand and contract. In tension and compression, the Young's modulus remain same. And then before going to derive it, first you should know the notation. R stands for radius, Ri stands for inner radius of the curved beam. Next, Rn stands for the radius of the neutral axis of the beam. Then Rc stands for central axis of the radius of the central axis of the curved beam. R0 stands for outer the radius of the outer fiber. Then with respect to the central axis, we'll call it as C1 and C2. C1 related to inner fiber, C2 is related to outer fiber with respect to central axis. Then with respect to neutral axis, you can call it as Ci and C0. The distance from neutral axis to the inner fiber, distance from neutral axis to the outer fiber. That's how do you remember is Ci. Ci stands for inner fiber, C0 is outer fiber from the neutral axis and central axis. Then the distance between the central axis and the neutral axis, that we represent E, eccentricity, right? These are the notation, you should know this. And when curved beam subject to an external bending moment, now how the stresses are occurred. Now here we consider a small element in from the neutral axis, a positive y direction. It's subject to what? Compressive, that is negative in nature. When you consider only the right side portion, when subject to with respect to AB, when beam is subject to an external bending moment, what happens? The CD will slightly turn, means above the neutral axis what happened? The dimension decreases, below the neutral axis dimension increases, means the change in element takes place. It decrease in dimension, increase in dimension. Now how much dimension is decreases here? That angle is called d theta. Here for this theta is the angle of the small portions what we consider this, right? Now these are the notations you can use, right? Then F is for instead of applying external bending moment, they give the applied force. Then later we'll discuss what is the L. L stands for the distance between the line of action of force on the central axis of the section. A is the cross-sectional area. Sigma stands for stress, direct stress, bending stress at inner fiber, bending stress at outer fiber. Combined stress. Combined stresses are nothing but what? Combined stresses are it is sum of direct stress and bending stresses. And maximum stress is always, you know, that half of the maximum normal stress. These are notations you should familiar, and with the formulas what we can see here, right? Now consider a small portion, consider a small element or strip at a distance of y, at a distance of y from the neutral axis. Then let dA is the area of the element. Now what is the original length of the element is, by taking, see this, by taking a center of a circle. How do you determine center of a circle? Is x is equal to r into theta. Same formula holds good for here. From the center of the center line of curvature to the neutral axis is r, and from neutral axis to the fiber small element is y. Now what is the total radius here? Rn plus y into theta. Now this is the original length of the element. Once you apply an external bend moment on right side, that is in counterclockwise direction, that is change in length of the element is a decrease in dimension. How much it decreases here? You can see that how much it decreases here. From here to here it is y, that is a radius. Angle is d theta. What is sector of the circle here? Y into d theta. This is a change in length of the element. As you know that what is strain induced in the element is change in dimension to the original dimension. Here change in length by original length. This is the formula you will get. Then our aim is to determine the stresses induced in the element. What is the stress is equal to? We know that according to Hooke's law, stress is directly proportional to strain. In order to remove the proportionality, we need a constant, that is Young's modulus. Why do we use negative sign here? Because the above the neutral axis, see the figure, the negative sign is above the neutral axis, fiber undergoes is compression, or the fiber is shortened. That's what is negative sign comes here. Then substitute the value of E. This is the formula get, keep it in this one, equation number 1. Then what are the forces acting on the element is, as you know that stress is equal to force per area. Stress is equal to force per area. From this force is equal to what? Stress into area. For element you can take as dF is equal to sigma into dA. Now substitute the value from the equation 1, substitute value of sigma. This is the what is the force acting on that element, you will get that is called equation number 2. Next, apply the equilibrium conditions. What is the equilibrium? Now apply the equilibrium condition. From condition of equilibrium, what is the condition of equilibrium? The summation of forces over the whole cross-sectional area, summation of forces over the cross-sectional area is equal to 0. You know the vector sum of all the forces equal to 0. Here the summation of forces over the whole cross-sectional area is 0. This is first equilibrium equation. Second equilibrium equation, the summation of the moments are nothing but what? Force into distance due to these forces is equal to the applied bending moment. First you apply the first equilibrium equation. According to force equilibrium, the summation, instead of summation you call it integration over the area, dF is equal to 0. Substitute equation 2 in here, then you simplify it. Now take the constant e theta by theta, take outside. The integration of y divided by Rn plus y into dA is the area integral. Now here I want to make left hand side is equal to right hand side. How do you make? If this term is become 0, then the solution will not exist. This becomes non-trivial solution. That's why this term should not equal to 0 because of non-trivial solution. Now what is the remaining term here? Integral of this term, remaining term is equal to 0. What this equation gives? This equation gives the neutral axis radius, that is Rn will give. This is the first equilibrium. Then go for apply second equilibrium equation. What is second equilibrium equation? The summation of the moments due to these forces is equal to the applied bending moment. As you know, the bending moment is nothing but what? Force into distance. We'll go apply the force into distance, the summation. Why the negative sign comes? See that in the figure on right side, what type of moment here applied? External bending moment. This is counterclockwise. That is a negative sign, right? Negative sign is due to because of counterclockwise movement. Then substitute the value of dF from the equation 2, then simplify, minus into minus plus, then take the constant outside is also area integral. Then now take the integral of y square by Rn y dA. In this, what is y square by Rn plus dA? Y square by Rn plus y. You can write taken it is y minus y Rn divided by R plus. So how do you consider this one? Consider as it is y minus y into Rn by Rn plus y. Now you simplify, take LCM, then you cancel the term. Finally you can write it as y minus y Rn by Rn plus y is also equal to y square by Rn plus y. You should remember this one. You should remember while deriving. Then take this, instead of y square by Rn plus y, you can call it as y minus y into Rn divided by Rn plus y. Now substitute in that previous equation, then simplify, apply the integral term. As you know that from the equation 3, integral of y divided by Rn plus y dA is equal to 0. The remaining term is, this is the term we'll get. Now what is the interesting point here? Integral of y into dA. What is integral of y into dA means? dA, area into distance. That gives a first area moment of inertia. First area moment of inertia, that is the area of the section into that eccentricity. The product of total area and the distance between the central axis and neutral axis. Then substitute here, that gives equation here, bending moment. But our aim is to determine bending stresses. From equation 1, what is equation 1? From equation 1, you can see this is sigma. From this we substitute E theta by theta. What is E theta by theta? Is equal to this for equation. Then substitute this E theta by theta is equal to in the above equation, equation number 5. Then simplify it. Finally get bending moment is this equation. Then from this our aim is to determine bending stresses. Sigma is equal to minus mb by a into y divided by Rn plus y. Why negative sign comes? We will consider above the neutral axis the fiber undergoes here compression. That's why negative sign is there. Now equation 5. This is the bending stress above the neutral axis. The negative sign represents that fibers are subjected to compression in nature. Now what is the general equation? General equation for the bending stresses in a fiber at a distance of y from the neutral axis. The bending stress is plus or minus mb by ae y divided by Rn plus y. This is equation number 25.53 in the data handbook volume 2. Design data handbook Bellinger volume 2, 25.53. If you now, so this is the important equation you should remember, or you can, by using sin data handbook, you can see that. Now what are now important one is bending stress at outer fiber. For outer fiber, what is the bending stress at outer fiber? What is the y value? Y value I can substitute y is equal to what? Substitute y is equal to c naught, plus or minus above the neutral axis is positive y direction is a plus c naught. For outer fiber y is equal to c naught. Substitute into the equation number what? 5. Substitute in the equation number 5. Now you will get this equation, then substitute wherever y is there, plus c naught, then you will get. Now we know that Rn plus C naught is equal to R naught. This is equation number 25.54. Similarly, at inner fiber, y is equal to minus Ci into the equation 5. Y is a negative sign here below the neutral axis and negative y direction, not negative y direction it is. That is negative sign. You will consider minus into minus plus. That is the formula. You will get 25.58. This is the bending stress at outer fiber. O stands for outer fiber, I stands for inner fiber. And other formulas you can see that. Then what are the stresses active? Direct stress as you know, the force by area, equation number 25.56. Bending stress, already we know that, plus or minus mb by a into y divided by Rn plus y, equation number 25.53. As you know, the combined stresses are the direct stress and bending stress, or plus or minus, or you can use only plus and bending stress. Direct stress and bending stresses. Now what are some of the properties? Here you consider only a rectangular cross section, but beams, curved beams are, it may be a rectangle, circle, square, T section, high section, etc. A triangular section also. Then you can extract some of the property, cross sectional property. Now you will refer the table 2.7 from volume 1, the property cross section table. From this corresponding cross section, take area area moment of inertia I and distance to the farthest point. Let us see from neutral axis to the from the central axis to the outer fiber C1 and C2. For other sections, some in the table you will not get the T and I section, unsymmetric I section. Then you go for remember this formula for other section such as T section and unsymmetric I sections. For the T section, see this geometry. For the T section, now this is the inner fiber. Always inner fiber is having thickness is more, outer fiber thickness is less. For T section, what will be the area? As you know that here portion 1 and portion 2. Area is vector sum of all the areas of the portion A1 plus A2. A is now the for rectangle question B into H. Finding CG. How do you find the CG? Here from outer fiber you consider here Y bar. How do you find Y bar? As you know that in elements of civil engineering, we know this formula is used for the different cross section. Vector sum of A into AIs and Y divided by summation of AIs. AI is where from 1 to n portions. This is the formula is used. From this, what is C1? C1 is from the central axis to the inner fiber H1 plus H2 minus Y bar. Outer fiber C2 is Y bar. Suppose if you want to calculate area moment of inertia, now this is a general formula is used. I think already you heard about elements of civil engineering and also in mechanics of material, right? Similarly, go for unsymmetric I section. Unsymmetric I section, this is not symmetric. It's a symmetric about y axis but not symmetric about x axis. This is unsymmetric I section. Then what is the area? Same formulas used here. Then after that, now you know that what is the design of curved beams. And one more I forget here, the sixth one. Now refer table 25.2 for the different types of cross section. Find Rn is the radius of neutral axis. Then remember this is also table. Okay, then as you know the design of curved beams, what is the design of emission element? It's an iterative process of assigning specifications of curved beams to withstand load or to do its function. What is specification of curved beam? This is shape, size, measure composition and methods and arrangement of parts. What are the shapes of curved beam? It may be a different machinery elements. You can use a C-clamp, crane, hooks, machine frame. What type of cross section it is? Is a rectangle, triangle, circular, square, T, I section, etc. Now what is the size? What we are going to determine here? Dimensions. Such as if rectangle cross section, what we are going to determine here? P, there is a breadth, height, and if you circular cross section, diameter. What is the metal composition? Usually the curved beams. For civil engineering, we use the building blocks. This for mechanical elements, we use a mild steel or cast iron. The arrangement of parts. What are the parts where how do they arrange here? These are them. Then the curved beams are subject to what type of loads? Usually the transverse load. The beams are subject to transverse loads and movements movements. And in another way, if it is beam is subject to eccentric load, that eccentric load is split into two. One is direct load and another one is a movement force into. From the direct load we will get direct stress. From the movement force into perpendicular you will get bending stress, right? Remember that combined stress is nothing but direct stress plus or minus bending stresses. Yes, thank you for watching this video, stresses in curved beams.